Circular motion is a special case of curvilinear motion in which the radius of rotation remains constant. Circular motion is described as a movement of an object while rotating along a circular path. In today's video, we are going to look into circular motion from two different perspectives. We are also going to look into centripetal acceleration and revisit the concept of instantaneous acceleration with some fresh and simple examples. My name is Shaunak and you are watching this video on my channel Physics for Students. A warm welcome to this fresh series of videos on Students' Guide to Classical Physics. Before we go ahead and start learning about circular motion, I would just like to give certain very basic definitions of circular motion so that the fundamentals, when they are made strong, the further studies become easy. So first of all, we need to understand a circular motion is, as I told, is a movement of an object along the circumference of a circle or rotation along a circular path. It can be uniform with a constant angular rate of rotation. Now you see I draw a line of this one. This is an object moves with a radius r, and then after traveling at a distance, the particle moves at this one, the green one, and I call it as the distance traveling s. It has moved at an angular displacement of theta equals to s by r. And theta, as you know, it is called angular displacement measured in radians. So for example, 2 pi radians would be equal to 360 degrees. So distance s, r is the radius, and this is just 2 pi radians equal to 360 degrees. Another important concept which comes right now is what is called tangential velocity. If motion is uniform, an object takes time t to execute motion, then it has a tangential velocity which is given v equals to s upon t. The capital T actually denotes time to complete one revolution. However, the frequency is the number of revolutions per second time. So v is the tangential velocity, t is the time, and the frequency is given as 1 upon t. We take a similar kind of a figure, but what we do is that here we take the position at time tf, which is equal to ti plus the movement delta t, and here is the green particle moving from this position to this position at time ti. This is the delta theta, that is the displacement, which is theta f, and this is theta I. So here we find what is called an angular velocity is equal to angular displacement upon time interval, which is theta by t. So uniform circular motion happens when omega is constant. Now here what we can do is that we can combine, yes, this is the omega turning its this direction. Here we can take the first equation, this one, the second equation, and the third equation, and we get what is called b equals to r omega. Now this is something just by substituting the values and getting the calculations, so you can just take it across. Okay, here is a small food for thought. I would call a question for you. If you want, you can just check your analytical skills, or you can leave it in the comment box. I will wait for your answer. If I get a beetle or a bug or an insect, just for example, which is placed on a record or a turntable which is moving uniformly, the first question is that, is the beetle's tangential velocity different or same at the different radial positions? This is one. Second, is the beetle's angular velocity different or the same at the different radial positions? This is just a food for thought. You can just put up your answer in the comment box of this video. I will like to check and we can talk about that. Here is a small hint coming up. Remember that all points on a rigid rotating body or a rigid rotating object will experience the same angular velocity. So I've just given a hint. If you find there's a beetle right on the turntable, you need to find out the tangential velocity. Is it different or is it the same? And same goes with angular velocity. Okay, so now we come to the central part of our video, that is, we are going to look into circular motion from two different perspectives. One is the geometrical and the second one is called the analytic. For the geometrical perspective, here are few of the lines and the vectors that we construct. Simple RT plus delta T RT, and this would be VT plus delta T VT. Okay, so what we do is that we let T prime equals to T plus, so yeah, this is in counterclockwise direction. So we let T prime equals to T plus delta T, and as indicated here, the position and velocity vector of the particle at time T. This is the position, the velocity vector at time T. At time, this is T plus delta T. Now here you see the picture is drawn in a moving in counterclockwise, but we shall soon see that the same acceleration is obtained for clockwise motion also. Note that 3r T plus delta T and RT have the same length r, and that V T plus delta T also have the same length v, since the speed is assumed to be constant. Furthermore, the angle between the two vectors, that is the r vector, is the same as the angle between two vectors. Why this is important? Because since these two vectors, the angles between them are the same, so that since at each instant v is perpendicular to r, the two vectors v vectors and the other vector r, they are perpendicular to each other. Okay, so we take the same figure, and there is a change. The change is that during the time delta t, the arc length has traveled this much, v delta t, and the radian measure of the angle between rt plus delta t and rt is d delta t upon r, quite same, because the distances between them are the same. So this is what is called the radian measure that we do. Okay, now what we do, we proceed with the same figure, but what we do is that we apply a little bit of trick. Now what is that trick? What we will do is that we will bring the tails of this one, Vt plus delta t, and this tail together by what is called a parallel displacement of either vector. Then what happens? We get a figure like this, right? Then delta v is the vector from tip of Vt to the tip of Vt plus delta t, this one, right? So what is that? The delta v is a vector from tip of Vt to the tip of Vt plus delta t. Okay, now the triangle, as you understand from your school level mathematics, is basically an isosceles triangle, and as delta t tends towards 0, the base angles of the isosceles triangles becomes right angles. Quite obvious, right? Because it is because delta t is moving towards 0. So what we see is that delta v becomes perpendicular to the instantaneous velocity vector v, and it becomes anti-parallel to r. So the magnitude, I would again repeat, the instantaneous, the delta v becomes perpendicular to the instantaneous velocity v and is anti-parallel to r. And what happens now is that the magnitude of the acceleration vector is given as this. That is a, we are taking the modulus limit of delta t tending towards 0, delta v upon delta t. Okay, now as we have seen this and this, these are the two isosceles triangles, and more or less they are what we can call they are similar. So what we have is delta v upon v is equal to delta r upon r. Quite obvious, this comes from the basic thing. But since the angles between this one, this red one, rt plus delta t and r of t is very, very, very small, the chord length of delta r can be replaced by the arc length, that is v delta t, and what we get is delta v equals to v square upon delta t by r. Sorry. So from here what we have shown, ultimately what is the bottom line, is that the acceleration vector has a magnitude of v square upon r, right? And is directed from the instantaneous position of the particle towards the center of the circle. Towards the center of the circle. So this is what we have seen, and this v square upon r is called what we call the centripetal acceleration, fundamental concept of Newtonian mechanics. Now, centripetal acceleration is something which is called the acceleration of a body traversing in a circular path. You can read out the definition. The acceleration is directed radially towards the center of the circle. The centripetal acceleration, whatever A upon A sub c or AC, has a magnitude equal to the square of the body speed, that is the v square. This is the very standard textbook, I would say, definition of centripetal acceleration. And the word centripetal means directed towards the center, and to remind us, this is the direction A. Okay. Now what we do is that we take an analytic. We have seen the geometric method, constructing vectors, how we come. Now we take what is called the analytic method of circular motion. What we do, we take the same circle, and here is that the vector from the center of the circle to the instantaneous position, and now what we do is that we use two vectors I and j. Now here what happens is that the vector from the center of the circle to the instantaneous position of the particle is this one, right? And here what happens, r and theta are the polar coordinates. So if the particle is moving in a circle here, if the particle is moving in a circle with a very constant speed, then dr upon dt will be 0, and obviously d theta upon dt equal to 0. Using these values, if we plot, so yeah, v upon dr upon dt will be equals to this one. Now if we take this equation further, we can use the calculus chain rule. So we get this. Now one thing which is very important, I have skipped certain steps, that the standard differential formulas require that theta can be expressed the theta can be expressed in radians. So it should be clear that v is tangent to the circle, right? Now because we know that v square equals to this, so therefore we have this. This is, I won't say it is an advanced calculation, but little bit a kind of a complicated calculation. For the sake of understanding circular motion, if you want to skip this one, you're absolutely welcome, no problem on that. Okay, now we come to the last part of the video, which is called instantaneous acceleration, another very important concept of Newtonian mechanics. I have explained that in my earlier video, you can just have a look, but I think that I can do a little bit better justice explaining things a little bit better. Okay, so this is just a quick recap. Acceleration is defined as the rate of change of velocity. So from t to t prime, it is defined as this, nothing great. These two, vt prime and vt, these are basically instantaneous values of the velocity times t prime and t. Instantaneous acceleration is defined as the average acceleration, where t prime is tending towards t, and since we know vt equals to dx upon dt, we can write this to avoid, and that is a shorthand of this. If you want to go a little bit more into this, click on the I button, because I have already given the previous video link. You can just check in. What is important is the definition of instantaneous acceleration. So if there is a particle A, right, has an instant t, right, has an instant t, it is instantaneous, remember, is equal to the value that the average acceleration calculated for an interval at time delta t, which includes the instant t, approaches as the interval of the time delta t gets smaller and smaller as it approaches 0. So we know that average acceleration is change of velocity upon change in time. What is the formula for the instantaneous acceleration? Remember, A is almost the same, except that we need to indicate that we are interested in knowing that the ratio of delta v to delta t approaches as delta t approaches 0. So what we are interested in knowing is what the ratio of delta v to delta t approaches as delta t approaches 0. So we can indicate using the limit notation, very simple, delta t tending towards 0 and delta v upon delta t. However, now we will use two instances of examples that things will become much more clearer. Okay, so first instance is that let us consider a particle whose velocity in meters per second at an instant t is given by 2v equals to 2t squared, right? So at 1 the velocity is 2 meters per second, at 2 the velocity is 8 meter, 3 it is 18, and so on. Now let us say that we want to find the acceleration of the particle at the instant t equal to 3s seconds. The first thing that we need to choose is an interval of time delta t, which includes the instant 3 seconds. Yeah, here it is. So that this interval of time delta t, remember, it starts somewhere at t1 and somewhere it ends at t2, such that t1 is less than equal to 3 seconds and it is less than equals to t2. Now for simplicity, just to avoid deep mathematical calculation, we will choose t1 equals to 3 seconds, so that t1 is as close as possible to 3 seconds, and delta t can be made smaller and smaller by choosing values of t2, so that it is close to 3 seconds. So t1 is close to 3 seconds, delta t can be made smaller. We select t1 equal to 3 seconds and t2 is greater than 3 seconds. Okay, so this is the first instance we have to do. Let us say that we want to find the acceleration of the particle at t equal to 3 seconds. So what we do right now is that we take t1 equal to 3 seconds and we have taken that. So here we take t1 and here we take t2, and what we do is that we just find out the delta t by subtracting one from the other, and we can calculate the average acceleration using this formula, right? So find the velocity, this one, this one, this one, and we get v1, and then we calculate v2, so on, and then we go back. So if you want to take I'm just pushing things through because this is just simple arithmetic, so you can just go through, and then we calculate this one, and then we get this, and we get this, and you can look into it. So what happens is that we get 12.2 meters per second square. That means when the interval time of delta t is between 3 seconds and 3.1 second, the average acceleration is 12.2 meters per second square. In the second instance, we choose even a smaller time, that is 3.001 second. So we start t1 equal to 3 seconds, t2 equal to 3.001 second, delta t equals to this one. So the velocity v2 at instant 2 would be equals to this, and it gives to something like this, 18.01. Let us consider 18.01 meters per second. The average acceleration is this minus this, and what we get is the value this, and further proceeding we get 12.002 meter per second square. So what do we deduce? I mean to say, what is the final conclusion? The other one, if you go back to the values, you see 12.22, and here what we get is 12.022 meter per second square. So what we are finding is that as delta t is getting smaller and smaller, the average acceleration seems to be approaching 12 meter per second square. So we keep choosing a smaller and smaller at infinitum, and we get closer and closer to 12 meter per second square. Now what we can also find out from this example is that instantaneous acceleration as a derivative. Now when I talk of instantaneous acceleration as a derivative, this is quite simple, as you will see here. This calculation which we just did, now if you want to make further calculation, make it almost similar to 12 meter per second square, that the equation goes something like this, right? The equation actually goes something like this. Now okay, yeah, it goes something like this. Okay, so here this one is called the derivative of v with respect to t, so we call it dv upon dt. The instantaneous acceleration is obviously the derivative of velocity with respect to time. We call it dv by dt, a, that is instantaneous acceleration. We also know that as velocity is the derivative with respect to time, we can write it as v equal to dx upon dt. Second, what we find is that instantaneous acceleration can be written as this, right? I mean to say, if you write it in the full form, and here we come that instantaneous acceleration is the second derivative of position with respect to time, and then we come to the final formula, just simplifying the above one, a equal to d square x upon dt square. So that brings us to the end of our today's video. we have explained a lot about circular motion, uniform motion, instantaneous acceleration, centripetal acceleration, and so on. In the next part of the video, I would be talking about motion of a freely falling body, space-time and coordinate system, and transformation of components of vector. This would be a little bit now more into transformation of coordinates and how things happen. So that's it for the circular motion and other parts. Do let me know about your comment in the comment section, and please answer to the question if you feel for answering it. Click on the subscribe button and click on the bell icon to get all the notification for physics for students. Please do click on like and put up your comments, because I would be eager to know how the series of this particular classical physics is going on. I will be soon back with another interesting video, but till then, please keep yourself safe, eat healthy, think healthy, and be healthy. Bye up till next time.
Thank you for watching this video. We appreciate your time and patience. If you want to connect with us and provide further feedback, comment, or suggestions, please email us at contact.physicsforstudents@gmail.com. You can also follow us on Facebook, Instagram, and LinkedIn. See you soon in the next video.